Welcome back to Intro to Machine Learning. In this lecture, we're going to discuss the perceptron. The idea behind this model and algorithm is to learn a weight for each feature. So far, we've talked about the decision tree, k-nearest neighbors, and k-means clustering. In the decision tree, we basically sort features by importance. In k-nearest neighbor, all features are equally important. And in k-means, similarly, all features are equally important because we're dealing with a geometric space. With the perceptron, we're actually trying to identify the importance of each feature and assign them an appropriate weight. Perceptrons are supposed to be biologically inspired. As we've gotten further and further away from the perceptron with neural networks and deep learning, we've gotten a little bit further away from the biological inspiration. Brains are made up of units called neurons. We'll use that same terminology when we're talking about perceptrons. And the rate of firing of a neuron tells us how activated it is. We'll also use this word activated or activation when we're talking about perceptrons and neural networks. It's really supposed to be biologically inspired. The idea is that we're building a network of neurons, but they're going to be artificial neurons instead of biological neurons. But really, it's not really that tied to biology, mostly because we don't understand how the brain actually works. So trying to model it is a bit of a challenge. What we're doing is creating a very simplistic model of the way that it works, and we're running with it. This is what our model is going to look like. It's going to have this green node, this one neuron, and it's going to have all these inputs to it. So we actually have directed connections here, and from the small blue nodes, there is a directed connection to the blue neuron. All of these blue neurons, all of these blue inputs are going to be features in the feature space, which is in D dimensions, right? We have D features. We talked about this in the last lecture. Our feature vector is going to be some vector x, which has x1, x2, x3, x4, and so on, all the way to xd. We're also going to have weights associated with each of these features, like we talked about a few seconds ago. And so we're going to have a weight for x1, which is w1, a weight for x2, which is w2, and so on, okay? And this neuron is going to sum these individual weights times these individual features, okay? This makes up our model, okay? We have features, we have weights, and we have finally this activation, which is going to be this sum inside of the green neuron. We call our activation A, okay? And if the activation is greater than 0, then we're going to output the positive class. Whether that's yes or it's 1, we're going to output that. And if it's less than or equal to 0, we're going to output the negative class. Whether that's no, that's -1, it's 0, whatever it is. Let's start with an example to get a sense of what we're doing. Here we already have the features and we have the weights. So our feature vector is 4, 1, -1, 3, and our weights are 1, 3, -3, and 2. We need to calculate our activation, and here's the equation for that. But all it is element-wise multiplication and sum. So it's going to be weight 1 times feature 1, which is 1 times 4, weight 2 times feature 2, which is 3 times 1, and then we have -3 times -1, and 2 times 3, which is going to give us 16. So our activation is 16 in this case. In this case, with an activation of 16, the output of our perceptron would be 1, or yes, whatever our positive class is. So what are these weights really? Let's look at an example to get a better sense of it. Here's some data we've looked at a couple of times now. We have 4 samples, we have 2 features, and 1 label. So our x1 and x2 would be sunny and greater than 90 degrees, let's say we have a weight 1 of 0. That would mean that our activation would always be the second weight times the second feature. So whether or not it was sunny would have no effect on the output. If we look at an opposite case where we have the first weight is very large, then we would always have a lot of weight on that first feature, so whether or not it was sunny. And unless the second weight was also equally large, we probably wouldn't take whether or not it's 90 degrees into account when making our decision about going outside. If we have a negative weight, it can have the opposite effect, where we basically care about the opposite of that feature as far as whether or not we should go outside. Here again, we see the activation function, and we know that if the activation is greater than 0, then we output the positive class, and if the activation is less than or equal to 0, we output the negative class. It's actually convenient to have some sort of threshold rather than 0, so some value t. Instead of having a value t, we actually add this bias term b. So we can keep all the math really nice by having this threshold still be 0, but we can use this bias term to have this same effect. Here's our model again. And now we can see that the neuron, which has the activation, now has that bias term in it. What are the parameters of this model? Remember, for the decision tree, we had the parameters as the things that were learned during training, right? The things that the training data provided information for. So that was going to be what questions that you asked, in what order, and the decisions at the leaves. Here we have access to these weights and the bias. The features can't change, but the weights and the bias can. How do we actually learn? We learn through error-driven learning. Okay, so every time we make a mistake, we update. And if we don't make a mistake, we don't update. This is an online algorithm. What does that mean? That means I learn one sample at a time. So I look at one sample and I either update the weights or I don't, and then I look at the next and so on. Here's the algorithm for the training. This is also provided in the textbook. It goes over it really nicely in pseudocode. You initialize your weights and bias with 0, and you have some maximum number of iterations. And then for every training sample, x, y, in the data set, which is this D, this bold D, you calculate the activation. And then you multiply the label by the activation. And if the label multiplied by the activation is less than 0, then we update the weights. And we use these two equations on lines 7 and 8 to update the weights. Again, we initialize the weights and bias to 0. For some number of epochs or until convergence, we do the following steps. So epoch is a special term that's used in this kind of training situation, and it means one entire run through of the data set. So that means one epoch is equivalent to seeing every training sample once. 2 epochs mean I've seen every training sample twice. Until convergence, that means you're no longer updating. You no longer have to do any updates. Okay, so for a certain number of epochs, we take each training sample, we compute the activation for that sample, and we update the weights if the label times the activation is less than or equal to 0. And we update them using these two equations. So we update W by adding the label times the feature, and we update the bias by adding the label. Okay, this seems really arbitrary, so let's look into it. Why do we update the weights and bias like? Here are those update equations again. Let's look at an example of when our model gets something wrong in order to see why these update equations make sense. Here we have a sample that has a label of -1 and an activation that's greater than 0. This means that we got it wrong. If our label is -1, we want to have an activation that's less than or equal to 0. What is our activation again? Our activation is going to be our weight vector dot product with the x, which is our feature, plus the bias. And we already said that it's greater than 0. Let's think of an example where we just have one feature and one weight. So we have W1 times X1 plus B is greater than 0. Okay, so we got it wrong. We need to update. Let's use the equations up top to update. We have W1 equals W1 plus the label times the feature, which would be -1 times X1. And then we update the bias with the bias equals the bias minus 1, which is the bias plus the label. That means our new activation the next time around, when we see this sample, is going to be W1 minus X1 times X1 plus B minus 1. All we did was substitute the equations on the left, on the bottom left, into the equation for the activation, okay? We reduce a little bit and we get this equation. We reduce a little bit more and we see that we have W1 X1 plus B minus X1 squared minus 1. Well, this is just our old activation minus X1 squared minus 1. So X1 squared is going to be a positive number because it's the square of anything is a positive number. Okay, we're not dealing with imaginary numbers here. So that means our new activation is going to be less than our old activation, right? Because we're taking our old activation and we're subtracting two positive numbers. So we're reducing our old activation. So that means our new activation is going to be closer to the label than our old activation was. That's the reasoning behind those weight updates. I would recommend that you work through the opposite case, that is when the label is positive and the activation is negative. This is the whole algorithm, okay? We want to randomize the order in which we look at samples when we run this algorithm. Let's run through an example. Okay, we have this data here. We have positive samples in green pluses and negative samples in red circles. We have 10 samples in total. And we start off with our weights and bias having a value of 0. Let's go for epoch 1. Okay, we look at the first sample, which is 3, 3. I've randomly ordered them here so you can see that sample 1 is in the top right, sample 2 is on the bottom towards the left. So we start epoch 1 with sample 1. This is 3, 3. Okay, and the label is negative. Let's calculate the activation. So I'm going to use subscripts for the activation here so we have a better sense of what's going on and we can keep track of everything. So the first activation that we calculated is on sample 1. And we get 0 because all of our weights of bias are 0. And we multiply the activation by the label and we see that 0 is less than or equal to 0. And so we have to update based on our rules. Okay, so we update using those equations on the top left of the screen. And we get a new W1, a new W2, and a new bias. Okay, now our values are going to be -3, -3, and -1. We move on to the next sample, which is sample 2. Okay, we calculate the activation, and we get 14. Well, we take 14, we multiply it by the label, which is +1, and we get 14, which is greater than 0, so we don't have to update. Moving on to sample 3, we calculate the activation, we get -4. -4 times -1 is 4, which is greater than 0, so we don't have to update. Sample 4 is 2, 2. Again, we calculate the activation, we see that it's negative. A negative times a negative is a positive, and again, we don't have to update. We take sample 5, and we get a positive activation, and again, we don't have to update. Sample 6, similarly, we get a positive activation, and we don't have to update. Sample 7, Again, we get a positive activation. Oh, sorry, negative activation. But this is good because this is a negative sample. So -7 times -1 is positive, and so we're good to go, no update. Sample 8 gives us a positive activation, which gives us a positive activation times label, which means we don't have to update. Sample 9 gives us a negative activation, which is what we wanted because it's a negative label. So again, we don't have to update. And sample 10 gives us a positive activation, which is good because it's a positive sample, and so we don't have to update. Now we start again. We start with epoch 2, okay? So we run the first sample in again, and now this time we actually get a negative activation, okay? Which is good because we multiply it by the label, which is -1, and we get a positive number, and we don't have to update. We haven't had to update in a while, and in fact, we haven't had to update from samples 2 to 10. We already tested them with these weights, and everything is good. And so we've converged, right? We haven't had to change the weights. So we're good to go. That's it. That's our final classifier. So every prediction is going to be W1x1 plus W2x2 plus B, which is -3x1, -3x2 minus 1. Okay? We can actually plot this by working through this equation and getting it into slope-intercept form, right? So we do that in a y equals mx plus b format, as so, and we can plot our line just like this. Okay, so that's going to be what our decision boundary looks like. We haven't really talked about decision boundaries yet, but we will touch on them as we continue through the course. W actually points perpendicular to this line, okay? To test the perceptron, we simply calculate the activation and apply the sine function. So if we have this test point, 0, 0, we calculate the activation, it's -1. We apply the sine to -1, and we get -1. So that's going to be a negative sample. The perceptron algorithm always converges if the data is linearly separable. So if we have data where you can draw a line in between the two sets, no matter what, the perceptron algorithm will converge. It may take a long time to do so, but it always will. It's a guarantee. In this case, the data is linearly separable, right? So that's why we were able to so easily identify the separating line and to identify the weights and bias. The perceptron is both a model and an algorithm. Unfortunately, it's poorly named in that way. The idea is that the perceptron really is just a single neuron with weights attached to it, okay? And the inputs correspond to the number of weights. And the algorithm is usually called the perceptron algorithm, and it's an error-driven learning algorithm. That's it for the perceptron. We'll continue to touch on other aspects of the perceptron as we continue through this course, but we're going to build on this and discuss neural networks and deep learning.